First, I'd like to thank the organizers for the opportunity to speak here today. My name is Marcel Lotz, and I work on cluster environments and how they quench galaxies. And I'm part of Andy's group in Munich at the University Observatory. I use the Magneticum simulations, a set of simulations we haven't heard much about in the past couple of days, but I'm not going to go into too much detail about the simulations, but I'm rather going to focus on the physics. Just as a short overview, it's an SPH set of simulations. It employs a mesh-free Lagrangian. And if you want to know more, I'd refer you to the website, magneticum.org, or any of these recent papers. I use box 2B and box 2, so pretty big boxes with a relatively small resolution compared to the smaller boxes, but I'm focusing on galaxy clusters, and statistics are more important to me. So I'm going to jump right in. I started off this project with the question of how do starforming and quiescent galaxies differ in their orbits? What you see here is the velocity anisotropy plotted as dependent on the radial profile. So for everyone that's not familiar with it, positive values mean tangentially dominated, positive values radial dominated, negative ones tangential, 0 corresponds to isotropy. What you see here is the total profile in the top and the split up between blue starforming and red quiescent in the bottom. What's very interesting, and there are a number of things interesting with this plot between observations and our simulations, is that for both observations and simulations, we find that the star-forming galaxies are radially dominated. So that means they're typically infall dominated, and that points at them being more recently accreted. So what we did next is look at how they differ in their line-of-sight phase space. So what you see on the left-hand side is the line-of-sight phase space velocity normalized to the clusters that we're looking at. You see the star-forming population on the left and the quiescent population on the right. The dots correspond to observations that we compare with, and the color map corresponds to the phase space density of multiple stacked clusters from the Magneticum simulations. And what you see is this complementary nature of these two populations. So in the inner regions, you are dominated by quiescent galaxies, whereas the outskirts have a much higher probability of having star-forming galaxies. So that's pretty much in line with expectations. But what's cool about the simulations is that we can look at the radial phase space, so at the radial velocities, and not only at the line of sight. So we can actually look at what's happening specifically with respect to the spherical geometry of these objects. What you see is, similar to the projected or line of sight phase space velocity, the majority are located in the cluster. But it gets very interesting when we look at the star-forming galaxies, and we see that the vast majority of star-forming galaxies are characterized by a negative radial velocity. So that means that they're infalling. They're in the process of infalling into these clusters. And there are some exceptions where some star-forming galaxies actually make it past their pericenters, but the vast majority of star-forming galaxies, independent of different redshifts and different cluster masses, get quenched during their first passage. What we also see is that there's a trend with cluster mass. So with increasing cluster mass, the quenching becomes more efficient. So in the top, you see that the radius to which the star-forming galaxies actually fall into before being quenched is higher, whereas low cluster masses, star-forming galaxies are able to penetrate deeper into the clusters. So one of the beautiful things about simulations is also that we can track individual galaxies and not just look at large statistics, but actually track the individual orbits. That's what you see here. So I'll take a second to explain what's happening on these plots. You see each line corresponds to a galaxy, a star-forming galaxy that we identified at redshift 1, and that we then, yeah, that's back, that we identified at redshift 1 and tracked until redshift 0. We then normalized this cluster-centric distance to the point of infall. So all these different trajectories were shifted on their x-axis to the point where they cross the virial radius, because we wanted to really see with what the orbits correlate. So if we move them all to the point where they fall into the cluster, we can maybe see some kind of underlying mechanisms and behaviors. On the left-hand side, you see the specific star formation rate independence of the cosmological time. And they've also been scaled to the point that infall corresponds to a t of 0. So there's a number of interesting things happening on this plot, but unfortunately I can't go into detail on all of them. I just want to make sure it doesn't go off again. But I want to focus on the time scales. So this top plot is just these average lines from this blueness measure, what we call it, scaled to its maximum value in the same interval. And the solid line corresponds to the low stellar mass interval that we look at, and the dotted line corresponds to the high stellar mass galaxies that we are tracking. What you see is that the low stellar mass galaxies don't really seem to notice the cluster environment until they really get close to it and until they fall in, and then they are rapidly quenched, which strongly points to ram pressure stripping being the dominant quenching mechanism for these low mass galaxies. In contrast, when we look at the high stellar mass galaxies, the dotted line here, they seem to already feel the cluster environment further out than is the case for the low mass galaxies. So you already see that they're quenched before they fall into the cluster, before they pass the virial radius. But once they fall into the virial radius, they also experience quite drastic, quick quenching. And there are a number of interesting things, for example, this tiny starburst. But if you want to know more about that, I'd invite you to talk to me later. So to really see what's happening and how galaxies behave and what's important in their survival or their prolonged star formation when they fall into the cluster, we looked at the subset of galaxies that remain star forming 1 gigayear after their infall. So we identified the galaxies that are still star forming in this region here, and only a subset is plotted here, so we have a bigger sample than you can see on this plot. And we looked at those and how they behave. And that's what we called survivors. So surviving galaxies are just selected to be star forming 1 gigayear after their infall. And so if you look at the top left-hand plot, this looks pretty similar to the previous one. But if you look at the bottom plot, we see that the orbits of the low-mass stellar galaxies are significantly shallower than is the case for the total population. So it seems that stellar galaxies in the low-mass area that we consider are more likely to survive if they're on shallow orbits. And this doesn't, to such a strong extent, apply to the high stellar mass galaxies. So we wanted to look at other factors that might help high stellar mass galaxies to survive. And for that, we just simply looked at the mean stellar mass of the total population and of the surviving population. And if you look at the bottom plot for a second, that's the bottom ones here, there's not a really significant difference in the stellar mass in the low mass bin. But if we look at the high mass bin, there's a factor of 4 difference in the high stellar mass interval. So the galaxies that survive are the ones that are very, very high in stellar mass compared to the total population in that bin. And that already brings me to my conclusion. There are 4 main points. Star-forming galaxies are quenched during their first passage, most likely by ram pressure stripping once they fall into the cluster. And there are other effects in the outskirts that I haven't gone into during this talk. But once they fall into the cluster, the dominant quenching mechanism is ram pressure stripping. Almost all galaxies are quenched within 1 gigayear. And if you want to survive in the low mass regime, you need shallow orbits. But if you want to survive in the high stellar mass regime, you just need significant high stellar mass to shield you against the quenching. And those are my 4 main points of this talk. Thank you very much for your attention. If you have any questions, I'd be happy to answer them.
How does the quenching depend upon the sizes of the galaxies? So that can you look comparatively for any given mass, whether the bigger ones, for example, get ram pressured more easily because they have extended disks, et cetera, et cetera?
It really depends how far we go down in our mass resolution, because the smallest galaxies we look at don't have morphologically resolved disks. So the disk would if we go to higher resolutions, they're more effective at protecting the galaxy against quenching for a longer period of time. But if we're in a low resolution where we look at the subgrid physics, it's not, the morphology isn't important, but rather just that subgrid physics. But if we go to a higher resolution, a disk is protected for longer.
I was wondering whether this 1 gig-year quenching is consistent with observations. Jeremy Tinker and Andrew Wetzel found that the intermediate mass galaxies typically survive for at least 2 gig years.
Yeah.
High and low mass galaxies are usually less, but still I'm not sure if you're... So have you compared to the data, and how does that agree? Also, a thing that everybody finds who looks at this is that the orbit really matters a lot.
Yeah.
The highly radial orbits that bring galaxies into the central region where they're going to be ram pressure stripped are, of course, much more effective at quenching.
Yeah, we find the same behavior with orbits. So we also looked at the anisotropy at different redshifts, and that's always the case, as you said. We look. Oh, I thought it went off again. No, I don't need it. It's fine. Yeah. Yeah. We haven't compared in detail the different timescales yet. I'm looking into that, and the next project after this is actually to do high zoom-in simulations and look at that in more detail and also resolve morphology to a larger extent than is the case in these cosmological simulations. So no, we haven't compared in great detail with it, but we've looked at a different group, and we've looked at different mass spins, not just this high and low mass spin. And there's very interesting behavior in that we haven't fully understood yet. So that's definitely still a topic of very active research.
So I'm actually had the opposite question as Joel. So observations of low mass galaxies, granted lower mass than what you're looking at here, but dwarf galaxies tend to have a much higher quench fraction as you go, at megaparsec distances from even like Milky Way mass galaxies. Marla Geha's work showed this. Yeah. So it's surprising to me that the low mass galaxies seem to be less sensitive to quenching far out in a denser region, where based on that work, I would expect the opposite.
So our explanation for that is especially starvation and pre-processing. So our high mass galaxies typically fall in groups. So they're already in an environment prior to infall that has a higher density than is the case for a lot of the lower stellar mass galaxies. I don't think we're talking about the same low mass. So my resolution limit is I look at galaxies over 3.5 times 10 to the 9. That's my mass cutoff in stellar mass. Most of the most massive galaxies fall in substructure. And small galaxies fall in substructure as well, but not as often as the large mass galaxies do. So the effect is stronger for the high mass galaxies.
So when you say they quench by ram pressure stripping, back here, do you mean the ram pressure stripping of the ISM directly, or of the galaxy halo and then strangulation takes place? I guess what's the detailed mechanism there?
So the detailed mechanism is really the intercluster medium that presses out the gas of the galaxies. And it's like we're looking into more detail on that. That's what we're going to use zoom simulations for. But what we already see now is that really the cold gas component gets pressed out of the galaxy, and then no more star formation can take place. Our measure of star formation is slightly different than from observers because we don't look at color, but we look at actually the star formation. So if something might still be blue for observers, it won't be blue in our simulations because we look at the actual star formation rates. So we might, there might be a discrepancy as a result of that.
The stripping of the ISM gas directly is what quenches from a galaxy.
I can't hear you.
We can talk offline. It's fine.
Yeah, okay.
Okay, let's thank Marcel again. Our next